In this video, we're going to get some practice manipulating the material balance for batch reactors by working through problem 3 of the Chapter 10 Lecture Problems worksheet. And so in problem 3, what we're doing is we're taking a batch reactor, which inside the batch reactor we have the irreversible liquid reaction going on, where some species A turns into some species B. Now, inside our reactor, initially we have a concentration of A that is Ca naught right here, and the volume of the reactor is V sub r. And I wrote here as a note that what we're going to do is we're going to assume V sub r is constant. And that's because we're dealing with a liquid reaction, so we're going to make the assumption that everything is incompressible. Okay? And so, based on these two pieces of information, what the problem wants us to solve for is it wants us to develop equations for the concentration of A and the concentration of B for the following two cases. One, where the reaction rate is equal to K sub 1 times the concentration of A, and in case 2, where the reaction rate is equal to K sub 1 times the concentration of A squared. In this video, we're going to focus on part 1 of this problem. And so based on the information in this problem statement, what I want you to do is to take this information and develop a process flow diagram. So pause the video here and do that. So based on the information in this problem statement, we could prepare a process flow diagram that looks like this. It's relatively simple. Once again, the batch reactor is one of the more simple, or the simplest types of reactors out there. Okay? And so what we have going on is we have our batch reactor here, where the volume of the liquid inside is what we're going to say is V sub r. Initially, the batch reactor has some concentration of A that's equal to Ca naught, so at time 0. And even though explicitly in the problem statement we didn't say this, the concentration of B is, we're not going to say it's Cb naught, we're going to say it's equal to 0. And we'll see how this affects the problem later on down the line. Okay? And so in this reactor, we have the reaction A goes to B. Alright? And so the problem statement wants us to derive equations that describe the concentration of A and the concentration of B as functions of time. And so what we're going to do here is we're going to start with deriving the material balance for species A. And there are two parts to this problem, but deriving this material balance, at least up until the differential equation, is going to be the same for both parts. Okay? And so for species A, we're going to write the general material balance equation. A is equal to I minus O plus G minus C. Okay? Since we are dealing with a batch reactor, there's no input or output, so these are 0. And for species A, there's no generation. That's equal to 0. It's only being consumed. So what that tells us is that our accumulation is equal to, the negative consumption or so. Alright? And so let's fill in what each of these terms are. For the accumulation, we want to deal with in terms of moles of A. So what we're going to look at is the change of the moles of A over time. So our differential equation is going to be dNA over dt. For the consumption term, it's going to be equal to the product of the reaction rate times the volume of the reactor. Okay? And so if we put these two things together, what we get is dNA dt is equal to negative R VR. Alright? And so that's just, using the material balance, we were able to already derive a differential equation. And up to this point, this is going to be the same for both parts 1 and part 2 of problem 3. Now, what we need to do here is we need to start filling in, what this reaction rate term is. Now, as far as, being able to do that by yourself, this is one of the goals, actually. This is one of the things you'll learn to do in the reactor design and engineering course in your senior year. Okay? So you'll learn more about how to derive reaction rate equations in reactor design. Okay? But for now, I'm just going to sort of guide you through how to derive these sorts of things. Okay? And so typically, the reaction rate is going to have the form where R is going to be equal to the product of a constant called K and then concentration raised to some power. Okay? And so I'm going to go through what each of these terms means. So the N here, this is what we call the order of the reaction. Alright? And so you'll hear terms thrown around like first order reaction, second order reaction, even negative order reactions. What that refers to is this exponent. So if you have a first order reaction, N is equal to 1, and then a second order reaction, N is equal to 2. Alright? I won't focus too much on that for now. I'm just telling you what that term means when you encounter it. Okay? And so that's what the N refers to. This K here, this is known as your rate constant. Okay? This is basically a term that describes how fast your reaction is going. Alright? And so this K here, what we have to pay attention to are the units for K. Okay? And so the units are going to be somewhat strange per time. Okay? And so the units for K, it's going to be per time, right? But ultimately, if we remember from the previous video, the units for our reaction rate have to be moles per volume per time. Okay? So if we're multiplying K by the concentration raised to some N, what we need to do is we need to make sure that the product of those two give us moles per liters cubed per time. And so depending on what N is, that's going to determine what the units of K are. And so we could just say that the units of K are L cubed over mole raised to the N minus 1 over time. And so if you think about that for a moment, you could see how that will always give you moles per liters cubed per time. Okay? In any case, so for part 1, what it wants us to do is it wants us to say that our reaction rate is first order, such that R is equal to K times CA. Okay? So that's fine. Alright, now if we plug that back into the equation, the material balance for species A, what we get is this, KCAVR. Alright? And so this is a true statement, but right now it's not so useful, right? Because we kind of seem to have a lot of variables here. We have CA, VR, we also have the moles of A. Alright, so what we want to do is try to reduce the number of variables we have. And one way we could do that is we could look at this moles of A term. Alright? And we could think about how it's actually related to the concentration in the volume of the reactor. And if we just do a unit analysis, what we could say is that the moles of A in a reactor are just equal to the concentration of A times the volume of stuff in the reactor. Right? So, if we rewrite Na in terms of concentration and volume, this is what we get. Alright? Now, another thing we could do is, in the problem statement, we're assuming that the volume of the reactants, or the volume of the reactor, that's constant. So that tells us that we could pull out this volume term from our derivative. So what we get now is dVr times the derivative of concentration with respect to time is equal to negative k Ca Vr. We have the constant Vr on both sides, so we could cross it out. And so what we're left with is dCa dt is equal to negative k Ca. Alright? And so this is the differential equation that we're going to work with. Alright, so I'm going to call this equation 1. Okay? And so, in order to derive an equation that describes the concentration of A as a function of time, what we need to do is we need to solve this differential equation. So, at this point, you should pause the video and think about how we're going to solve Ca. Okay, let's now solve this differential equation. Now, based on the review video, we could see that this differential equation is separable. So, 1 is separable. Okay? And as you remember, that means that dCa dt can be described as the product of two functions, where one function is a variable of Ca, and the other function is a variable of t. And so based on our equation 1 over here, what we could say is that our f of Ca is just going to be Ca, and our g of t is just going to be negative k. There's not really anything explicitly a function of t, so we could just say it's equal to this constant. So what we need to do now is we need to move all the Ca stuff to the left-hand side, and we need to move all the t stuff to the right-hand side. We're now going to integrate. So we're going to integrate dCa Ca, and we're also going to integrate negative k dt. Alright? We're going to do an indefinite integral. And so when we integrate the left-hand side, what we get is the natural log of Ca. And when we integrate the right-hand side, we get negative kt. But since we're doing an indefinite integral, we also have to remember to include a constant. So this theta naught, I'm going to say, is just some integration constant. And the reason I'm doing an indefinite integral rather than a definite integral is because, in my opinion, it makes solving for the unknown variables in a differential equation a bit easier. It's a bit easier to manipulate. Okay? In any case, we want an equation that describes C of A as a function of time and not the natural log of C of A. So what we're going to do is we're going to rearrange the equation. So I'm going to go to the next page here and just isolate Ca on the left-hand side. And in order to do that, what we need to do is multiply both sides, or take the exponential of both sides. So what we end up is Ca on the left-hand side, and for the right-hand side, we have the exponential of negative kt plus that constant. Based on our exponential rules, we could rewrite the equation like this. And so this first term, that's a function of t. But this term over here, it's the exponential of a constant. Okay? And so what that gives us is just another constant. Okay? So I'm just going to simplify it even further and now say that our C of A equation is equal to some theta, the exponential of theta naught, I'll just call theta, times the exponential of negative kt. So I'll emphasize that this is some constant. Alright? But we don't know what this constant is yet, so we need to figure it out. So at this point, pause the video and think about how we could figure out what this theta constant is. To solve for our theta constant, what we need to do is at this point, we need to apply the initial conditions for our system. So let's use the initial conditions to solve for theta naught. Okay, so our initial conditions, I'll box it in here. What we're told in the problem statement is that the concentration of A is equal to some Ca naught at time is equal to 0, at some initial time. So we could take this initial condition and we could plug it back into our equation in order to solve for theta. So Ca at time is equal to 0 is equal to Ca naught, which is equal to theta times the exponential of negative k times 0. So the exponential of 0 is 1. So that tells us that theta is just equal to Ca naught. So if we rewrite our differential equation, what we have is Ca is just equal to Ca naught times the exponential of negative kt. This is the equation for Ca that we derived. But of course, we need to make sure that this equation is correct. So how can we do that? How can we make sure that the concentration of A equation that we derived is correct? Pause the video here and think about how we could do that. To determine if our concentration equation is correct and actually describes our system, what we need to do is we need to make sure it satisfies the initial condition and also our differential equation. So let's first check the initial condition, which was that at time is equal to 0, our Ca was equal to Ca naught. So let's check that out. So for our concentration equation, what we have is Ca naught times the exponential negative k times 0, and that gives us back Ca naught. So our equation satisfies the initial condition. Let's now see if it satisfies the differential equation. So what we have is dCa dt. So let's take the derivative of the equation that we derived. And so our derivative here is going to be Ca naught. That's a constant. And then it's going to be times the derivative of that exponential term. And so based on the chain rule, what we get is negative k times the exponential of negative kt. I'll rewrite what we get on the right hand side like this. And we know that this product of Ca naught times the exponential of kt, negative kt, that's just what we derived for Ca. So in the end, what we get is negative k times Ca. And that is the differential equation that we started with. So our equation also satisfies that statement. So we could have some confidence that the concentration equation that we derived here is accurate. We have our equation describing the concentration of A. Let's now move on to deriving the equation that describes the concentration of B. So to do that, let's go to the material balance for B. We'll start with our general material balance equation. A is equal to I minus O plus G minus C. We're still dealing with a batch reactor, so there's no input or output. We are generating B, and we're not consuming it. So that's going to be equal to 0. Okay? Now, for our generation term, so just to write it out, that tells us that our accumulation is equal to just the generation term. So, let's write out what each of these terms are. So for accumulation, what we're going to be looking at is the change in moles of B per time. And just to jump ahead here, we could apply the same sort of logic that we applied for species A, where we could say the moles of B is equal to the product of the concentration of B times the volume of stuff in the reactor. And assuming that the volume of stuff in the reactor is constant, then we could write this statement. For the generation term, it's equal to the reaction rate law for this reaction times the volume of the reactor. And the reaction rate law is the same as it was for species A. So it's K times Ca, and that gives us K times Ca times Vr for our generation term. So if we put together our material balance, what we have is Vr dCb dt is equal to Kca Vr. Volumes on both sides, so they cancel out. And so what we have left here is dCb dt is equal to Kca. Now, it may seem kind of strange that our differential equation for Cb, for species B, is a function of Ca here, right? But at the end, what we have to remember is in the previous section, we derived an equation for Ca. And so what we could do here is we could actually just plug in what we derived for Ca. So we have our K here, and then what we derived for Ca was that Ca was equal to Ca naught times the exponential of negative Kt. And by doing that, we reduce the number of unknowns that we have. Okay? Alright, and so at this point, our goal is to derive an equation that describes the concentration of B as a function of time. So pause the video here and think about how we're going to solve the differential equation we have now. Our dCb dt equation can be solved because it is still separable. So we could use the same techniques that we've been using thus far. So to solve Cb, we should describe its differential equation to be separable so that it's a product of some function that's a variable of Cb and some function that's a variable of time. Okay? For the Cb term, there's nothing explicitly, there's no explicit Cb variable on the right-hand side. So we could just say this is 1. And then for the g of t part, what we could say is that it's basically equal to everything on the right-hand side. K, Ca naught, exponential of negative Kt. So to solve this differential equation, we'll move all the stuff, the Cb stuff, to the left-hand side, and we'll move all the t stuff to the right-hand side. Exponential negative Kt dt. Right? We're now going to take an indefinite integral of both sides. So we'll integrate dCb on the left-hand side, and then we'll integrate all this stuff on the right-hand side. Okay? And so the integral for the left-hand side, we're doing an indefinite integral, remember, is we just get Cb. For the right-hand side, it's a little bit messier of an integral. But fortunately, these two things are K, Ca naught. Those are constants, so we could just pull those out. And we just need to take the integral of the exponential of negative Kt. Alright? And so the integral for that, the integral of an exponential is just the same function back. But because our variable is on the inside of the exponential, we also need to remember to apply the chain rule here. So what we end up is with a negative k on the bottom. And since we did an indefinite integral, we also have to remember that we have to include some sort of integration constant here. Okay? In any case, so what we have is a k over a k, so those cancel. And so we could simplify our equation by saying the right-hand side is just equal to negative Ca naught times the exponential of negative kt plus some constant. Okay? But at this point, we need to figure out what that constant is. Alright? And all this is equal to Cb. To figure out what that constant is, once again, we're going to apply initial conditions. So I'm going to go to the next page here. And we're going to write out our initial conditions for species B. And what we could say is that Cb is equal to 0 at some time 0. So let's plug in that initial condition into our equation. So Cb at time is equal to 0. It's equal to 0 here. And so on the right hand side, what we have is negative Ca naught times the exponential of negative k times 0 plus some constant. This term here is just 1. The exponential of 0 is 1. And so if we solve for our phi naught, what we get is that it's just equal to Ca naught. So if we go back to our Cb equation, what we have is negative Ca naught times the exponential of negative kt, and then plus that constant, which we found out is just Ca naught. And so if we rearrange this, what we have is that Cb is equal to Ca naught, and then after factoring that out, we could say it's Ca naught times 1 minus the exponential of negative kt. Of course, we need to check to see if this equation that we derived is correct. So to do that, let's see if it satisfies the initial conditions and also the differential equation. So our initial condition was Cb at time is equal to 0. We'll plug it into our equation. We'll plug in t is equal to 0 into our equation. This is 0 here. Okay? And so what we get is Ca naught times 1 minus the exponential of 0, which is 1. And so that gives us 0. So it satisfies that. Let's now check the integral. Okay? And so the integral of our equation, even keeping Ca naught outside, we only have to worry about the stuff on the inside of the parentheses. So the derivative of 1 is 0. And the derivative of the exponential, if we apply the chain rule, is we get negative k times the exponential of negative kt. This gives us back k Ca naught exponential of negative kt, which we know from dealing with species A that this part is just Ca. So what we get back is the derivative of Cb dt gives us kCa, which satisfies the differential equation. So that gives us confidence that our Cb equation is correct. So we could say Cb is equal to this. Now that we've derived these equations for Ca and Cb, the last thing I want to do, even though it's not explicitly written in the problem statement, is I want to plot the behavior of these equations. We have these equations as a function of time, so let's see how Ca and Cb behave as a function of time. So I'll rewrite both of our equations here. So Ca is equal to Ca naught times the exponential of negative kt, and Cb is equal to Ca naught times 1 minus the exponential of negative kt. Okay. To plot these things, what I suggest we do is we should look at the extremes of the limits of each of these equations, so that when we're drawing our plots or sketching the behavior of these equations, we know what 2 points we need to connect. Okay? So from our initial conditions, we know that CA at time equal to 0 is equal to some CA naught. And we know the CB some time equal to 0. We just said that was 0. So that's one end of our spectrum. Let's now look at the other side. What happens if we let time be really large? So essentially let it be infinity. And so what we're going to get if we just plug into our equation is CA naught, the exponential of negative k times infinity, which is infinity. And so what we're left with is an exponential to the negative infinity, and that is 0. So the limit at time goes to infinity for CA is that it's basically 0. For CB, let's apply the same sort of limit analysis. So we have CA naught times 1 minus the exponential of negative infinity. So the exponential term is 0, and what we're left with is CB at very large times approaches CA naught. Okay? So when we sketch out our plots, these are the two limits that we should connect. So let's start with CA. Let's sketch a plot for that. And so here are our axes, where the y-axis is CA, and the x-axis is some sort of time. Okay? And I'll mark out the corner here, that's going to be 0 for both axes. And up here, on the y-axis, we'll say that's CA naught. And I'll say time approaches infinity as we go to the right here. And so when we sketch out the behavior of A, we could draw a point here at CA naught at time is equal to 0, CA is equal to CA naught. And then as time goes to infinity, CA approaches 0. And since we have an exponential function, or an exponential of essentially negative t, what we're going to have is an exponential decay. And so the concentration of A in our batch reactor is going to decay over time, and it's going to approach 0 as time goes to infinity. Let's now draw a similar sort of sketch for CB, where the y-axis is the concentration of B, where I'll draw that this value is CA naught. The x-axis is time, where on the left it's 0 here, and on the right time approaches infinity. At time is equal to 0, the concentration of B is also equal to 0. And then as time tends towards infinity, our CB approaches a value of CA naught. And so what we have here is an exponential, well, not quite an exponential increase, but it's a 1 minus an exponential. And so what we get is basically the flip version of the CA plot, where CB increases, but then approaches a sort of plateau value. Okay? And so by deriving these equations, we get a sense of how the concentration of species A and species B are changing inside our batch reactor as a function of time.